Okay, chapter 29. So you probably remember the discussion we had about black body radiation. Every object in our universe is a black body. A black body is an object that emits energy, emits energy in the form of electromagnetic radiation, and absorbs it. Electromagnetic radiation, and there were people that tried to describe the intensity of that radiation in terms of the wavelengths or the band of wavelengths of the light being emitted, and the temperature. Typically, the higher the temperature, the more electromagnetic radiation you're going to be emitting, the higher the intensity, and the broader the range of frequencies, or the broader the range of wavelengths. Okay, so if I were to have light being emitted from a pot boiling on the stove, say that's my radiating body. It's radiating light and all. We can't really see it because it's in the infrared range. Say it's cool. Say it's like cool, like maybe 70 degrees Fahrenheit, okay, or 25 degrees Celsius, okay. So if I were to look at the profile of the light coming out, if I were to look at all the different wavelengths of light at that temperature, I would get this distribution. Okay, I would get a lot that are surrounding a certain wavelength, whatever that wavelength may be for this temperature. What did I say? 70 degrees. Let me say 237 degrees Kelvin. 273 degrees Kelvin. Now that's 300 degrees Kelvin is room temperature. Okay, 300 degrees Kelvin. Okay, so I'm going to get a peak around a certain lambda, a certain wavelength of light, but I'm going to get other light at other frequencies emitted from my pot sitting on the stove. Okay, and they're going to trail off in this direction, trail off in this direction. I'm not going to have so much. Say maybe this is infrared, this is shorter, so that's sub-infrared, and then I'm going to go sub-infrared, sub, and then in this direction I'm going to get above infrared, shorter wavelengths, visible light spectrum, and so forth. So not so much visible light, not so much UV, not so much X-ray, certainly not any X-ray or gamma ray. All right. As I heat this pot up, as I heat this black body up, it's going to emit more electromagnetic radiation. There's going to be a higher peak here. The intensity of the light at lambda is going to be higher, and lambda might even shift. I mean, this peak might even shift towards the higher frequencies. But it's certainly the profile is going to spread out. So this is say 400 degrees Kelvin. As I heat this thing up, heat it up, we're going to start to see the pot turn red. If we heat it up more, it'll turn orange. Heat it up, if we make it extremely hot, it will turn white. Why is it white? Because this distribution is almost flat. It means it's pretty much emitting every frequency or every wavelength of the visible light spectrum, certainly a lot from the infrared spectrum, and probably starting to emit light in the ultraviolet. Why? Because this thing is made out of atoms, and atoms you can think of them as oscillators, okay? The first guys that came up with this picture had an equation that was, they were Rayleigh genes, and they had an equation that describes the intensity of this profile with as lambda something proportional to lambda over 4, lambda raised to the 4th power. Okay, that didn't work for us because when lambda goes to 0, it blows up. What Max Planck did was he came by and he said that these black bodies are emitting light at certain quanta of energy. The light that they emit is emitted in quantized packages, and he came up with this equation. Okay, it involves it's in some of the books, you can find it, but it involves the quantization of light. It's E raised to the energy like HF divided by, I think, beta T minus 1 or something like this. But anyway, in order to come to this conclusion mathematically, he had to make the assumption that energy was quantized, that the energy being emitted from black bodies was quantized. So that's what this equation here states. Quantization of energy, 29.1. That's where that comes from. Okay, but you're not going to be using that so much. But it's starting. This is the beginning of quantum mechanics. Okay. All right. So there were some other experiments that came after that built on this idea of energy being quantized. Okay, one of them was the photoelectric experiment, or the photoelectric effect. Okay, and again, what is this about? Building on the idea that energy is quantized. Okay, small amounts. So what is the photoelectric effect? What does it have to do with it? It's the effect that it's an effect that involves the interaction of light with material. More specifically, the energy of light with a metal, the surface of a metal. So let me draw the metal here. This is just any typical metal. Then you have light coming here. And what happens in the photoelectric effect is that light comes down here, it strikes an atom in the metal, strikes an electron. That electron gets some energy and it gets kicked out of the surface of the metal. All right? And this is the electron's energy, Ke sub E. And this is the photon's energy, E photon. Okay? And what they observed was that depending on the metal, if I just kept the same photon, in my experiment, I just kept hitting the metal and keep changing the metals, the amount of kinetic energy of the ejected electron would be different depending on the metal. Okay? Well, where does the electron get the energy to break away from the metal anyway? It gets all its energy from the photon. And as we were saying before, the energy of the photon is described by just this simple equation. Max Planck's constant times the frequency. All the energy that this electron gets comes from this photon. So the energy that it has is this photon minus the energy that it took to break it away from the metal, which is that W naught. Okay, so that's all the photoelectric effect is. And this W naught is an intrinsic property of the metal. For iron, it's something. For tin, it's another. For tungsten, tantalum, it depends on what the metal is, okay? So the amount of energy that your electron has after it's kicked out by this photon is going to be the photon's energy minus the work function. That's what they call this. This W is called the work function of the metal. Okay? So let's work a problem from that real quick. Photons and the photoelectric effect. All right. Electroviolet light I'm going to do problem 3. Problem 3. From what is this chapter? 29? What is this chapter?
29.
29. Okay, thank you. All right. Ultraviolet light with a frequency of 3 times 10 to the 15 hertz strikes a metal surface and pops out an electron. It ejects an electron that has a maximum kinetic energy of 6.1 eV. What is the work function of this metal? Okay, so here we are again. We know that the energy that the electron gets to be freed, that frees the electron from the surface of the metal, comes from the photon. Okay? Now, it would get all the photon's energy if there was nothing holding it there. But because there is something holding it there, the photon has to give up a little bit of energy. So the electron doesn't get all the energy of the photon. It gets the energy of the photon minus the work function of the metal. So this is what we have here. We have an ultraviolet light. Ultraviolet light with that frequency hits a metal surface. So they're giving us the frequency here, which is pretty straightforward. So this is Planck's constant, 6.63 times 10 to the negative 34 joule seconds times the frequency of this light. So this is all the energy we have to work with, whatever that multiplies out to be. 3 times 15 times 6.63 to negative 34. This turns out to be 19. This turns out to be 1.98 times 10 to the negative 18 joules. So that's all the energy we have to work with. Whatever the electron is going to have is going to be less than that. Okay? So the photon comes in and it gives this electron this much energy. So some of that energy is used by the work functions, consumed by the work function of the metal. Okay? So what we're left with is WHF minus the work function. So we calculated what the energy of the photon is. Now we're just going to subtract the work function of the metal. Work function of the metal is 6.1 eV. Now that EV is a different. I'm sorry.
That's the kinetic energy.
Yes, that's the kinetic. Thank you. That's the kinetic energy that the electron has. So that's 6 eV is that minus the work function of the material. Now we've got mismatched units here. We calculated the energy of our photon in joules, and the energy of our electron that got kicked out is in eV. But that's no problem. The conversion factor is 1.6 times 10 to the negative 19. Now you got joules on this side. So 6.1 times 1.6 times 10 to the negative 19 is 9.76 times 10 to the negative 19. Why is that? Because 1 eV equals 1.6 times 10 to the negative 19 joules. That's our conversion factor. So the work function of the metal is just this minus this. Okay? So that minus 1.10 to the negative 18. So I get the work function for that metal is 1.04 times 10 to the negative 18 joules. That's what I get. 1.04 times 10 to the negative 18 joules is the work function for whatever that material is. And that can help you identify what the metal is, because every metal has its own work function. All right, so that's the photoelectric effect. Okay, so what did I want you guys to know? I wanted the photoelectric effect, the Compton scattering, de Broglie wavelength, and Heisenberg uncertainty. So let's get on to de Broglie wavelength. Okay, another strange idea from quantum mechanics. Okay, so we're building on this idea of energy being quantized and light and particles acting like waves and waves acting like particles and having, you know, particle characteristics. De Broglie, we talked about this in class with, you know, if a particle, so I'm going to erase this if that's all right. So if a particle acts like a wave, well, a particle has a mass, it can have a velocity, it can have a momentum, and it's localized, and you know, there's certain ways we describe certain attributes that point particles have, and then there's certain attributes that waves have that particles don't. I mean, waves are non-localized. This goes off to infinity that way and infinity that way. It has a wavelength. Particles don't have. I mean, particles is just a point. It's got dimensions, x, y, z. It's width, length, height. Okay. Wavelengths have amplitude. Waves have amplitude. Waves have wavelength. Waves have frequency. So how can a particle, if it's going to behave like a wave, what is the wavelength of a particle? Okay. We didn't have a way of thinking about that, I guess, until de Broglie. He said, okay, well, the wave, okay, particles behave like waves. What's the wavelength of a particle then? That was a big question mark for a while until he came up with this. Just in simple, the path by which he got to this, I'm not sure of. But he said that the wavelength of a particle is related to its momentum. Simply related to its momentum. According to this equation, it's Planck's constant, where Planck's constant equals 6.636 or 26 times 10 to the negative 34 joules seconds over the particle's momentum. So if you can calculate the particle's momentum, you're fine and you're there. Or a particle's momentum is its mass times its velocity. Okay. So that means if I have a baseball and I throw it at 30 meters per second. Okay, so say I throw this baseball at 30 meters per second. This ball has a de Broglie wavelength. It doesn't behave like a wave. I mean, you can put spin on it, and you know, waves don't have. You can't throw a curve, but this has a wavelength, and we can calculate the wavelength of this. If we know the mass of the baseball, and we know its velocity, 30 meters per second, say its mass is half of or maybe a quarter of a kilogram, we can calculate its momentum. Its momentum is P, is just m times v, okay? And so that would be 1/4 of 30 kilograms